Hello, my name is Jeff Hittinger. I am the Director of the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. But more importantly for the proceedings today, I am a proud alumnus of the DOE CSGF program and the chair of the Frederick Howe Scholar Award Committee. Dr. Howes managed the DOE's Applied Mathematical Sciences program during the 1990s and was a strong supporter of the DOE Computational Science Graduate Fellowship. The Frederick A. Howe Scholar in Computational Science Award was founded to honor his memory and service to the computational science community. One or two Howe Scholars are named each year from the recent graduates of the program based on their outstanding leadership, character, and technical achievement. This year, we honor 3 recipients, 1 2020 awardee and 2 for 2021. The selection committee is pleased to name Dr. Thomas Anderson, a 2021 Frederick A. Howe Scholar in Computational Science. Thomas earned a PhD in Applied and Computational Mathematics in August 2020 under the supervision of Professor Oscar Bruno from the California Institute of Technology. After graduation, he joined the Department of Mathematics at the University of Michigan as a postdoctoral assistant professor. Thomas's selection as a Howe Scholar reflects both his exceptional technical achievements as well as demonstrated leadership and character. Thomas's doctoral thesis was focused on theoretical and computational problems for time-domain wave scattering problems on general domains. Thomas developed computational methodologies that rely on applying fundamental solution techniques and transform methods to solve frequency domain integral equations. The solvers he created possess a range of highly favorable computational properties, such as no dispersion in space and time, high order accuracy, highly efficient parallelization, time leaping, and solution sampling for large times at low cost. Furthermore, his novel methods offer these highly favorable characteristics at a reduced computational cost in comparison to other techniques in the field. Thomas's numerical approach has led to a new theoretical perspective on the decay problem, which has extended the state-of-the-art in scattering theory to configurations with challenging but ubiquitous trapping obstacles. Thomas's scientific contributions have enabled the solution of time-domain problems of scattering by highly complex structures, such as full aircraft, with unprecedented efficiency and accuracy. Thomas has also distinguished himself through service and leadership to the community at large. He volunteered as a mathematics tutor for middle and high school students from disadvantaged backgrounds through Caltech's RISE program. As an inaugural applied math representative on his department's Graduate Student Advisory Council, he worked proactively to ensure effective communication between the graduate student body and the department's leadership, improving student-focused activities and aiding junior colleagues during recruitment and visitation days. Thomas also engaged with and encouraged undergraduate research. In addition to mentoring an undergraduate student researcher, he co-created an undergraduate seminar course on ethics and social responsibility in science and engineering, with a focus on data-driven methods. Thomas also served as an executive officer of the Caltech Tango Club, where he taught, fundraised, and organized events and practices for the students. Thomas Anderson is a computational scientist who not only excels technically, but also takes on leadership roles in the scientific community and society at large. He embodies the qualities Fred Howes promoted in all early career scientists.
Thank you for the introduction. Today I'm going to talk a little bit about my thesis work and things I've been working on in this vein since then. I want to thank the Department of Energy and the Krell Institute first off, and I want to really thank the fellowship and the alumni that I've met over the years from whom I've learned so much. My thesis advisor, of course, and my mentor at Michigan, Shravan Panini, Sonia Kulev at Livermore as well, and a variety of others who have contributed importantly to my mathematical life. If I have an agenda today, it's to share with you that there are still some questions in applied math that can be answered using classical analysis, numerical analysis techniques, and obtain enhanced understanding of physical problems. And that is to say, machine learning hasn't put us all out of a job quite yet. So my universe here is time-domain linear partial differential equations. We're going to be looking at the scalar wave equation with Dirichlet boundary conditions. That is called sound-soft scattering in the acoustics literature. But of course, there's generalization to Maxwell's equations and other linear wave problems. So this is an important classical problem, and there are applications in a variety of scientific areas. One I'll just draw out in particular is propagation in dispersive materials, where your wave speed c actually depends on the frequency of the wave that is propagating through it. And this is an area that our methods apply very naturally to. But the wave equation in general is a classical problem, and there have been a variety of techniques that have been proposed to tackle it. I'm going to mention a few, and then I'm going to describe how our methods break from the past in some ways. So the basic problem is what I've shown on the right, where you have this wave that is going to propagate from left to right, top to bottom, and it's going to impinge on this inclusion in the background media, and it's going to result in some scattering. So the question is, what is the wave going to do as it hits the scatter? And of course, there aren't closed form solutions to this PDE for this geometry, and so we have to do this computationally. So being a classical problem, there are a variety of techniques. Volumetric methods would be the one that we would learn in a numerical analysis class, and that is the simple thing where you step forward in time, one step at a time, using the information from the previous time step. Now, I will mention that in doing so, you automatically incur an increasing cost for large time. You also incur an increasing error for large time, since at every time step you're making certain approximations. There are other issues that have to be addressed for volumetric methods, such as when you're solving an exterior geometry, you have to somehow truncate this to some finite region to do computations on, and this can be an important source of error. Time-domain integral equations are another broad class of methods, and this works using integral equations. I'm just going to provide a little bit of background here, that when you have a linear differential equation, you have a fundamental solution, and the solution to the PDE can be obtained using a convolution of the free space Green's function with some surface density phi. And this automatically gives you a solution to the PDE everywhere in the volumetric region that you might be interested in. But to satisfy the boundary conditions, additionally, you must satisfy a certain integral equation. And that's what I've shown on the left. To obtain the phi that satisfies this integral equation, you have to step through time. And in doing so, you have to integrate these integrals over the time history. This actually has to be done very accurately, or you will lose stability. And to do so accurately is challenging because one has to integrate over non-polytopic regions of space-time in multiple dimensions. So this can be challenging. Convolution quadrature takes a different approach. There's still a time marching method at play, but in addition, there's something called a Laplace transform, or discrete Laplace transform that is applied that transforms the time-stepping method into a decoupled modified Helmholtz problem set. And each element of the set can be solved independently, and then the solutions can be synthesized to produce the time-domain solution. So there are, again, two sources of error here. There's time-stepping error, and then there's contour integral error. The C transform actually has to be inverted using a contour integral, and this can be an important source of error that's been studied recently. So all these methods that I've just described incur increasing costs and error for large time, and we would like to avoid these issues. And to do so, we're going to take a slightly different tack. We're going to use Fourier frequency time hybrid approach. And what this means is we're going to Fourier transform the incident wave. What we're doing is very simple conceptually. We're Fourier transforming the incident wave. We solve scattering problems for each individual frequency, and then we inverse transform. Now, of course, the important questions to address are, one, how many frequency domain problems need to be solved, and specifically the relationship of that number to the duration of the incident field. For the inverse transform, a similar question, if we want to evaluate this solution in time domain at some very large time, what is the relationship of that number of frequency domain problems that need to be solved for that time? And I'll mention that this basic approach has been done before, and generally people have noticed that one needs to solve an increasing number of frequency domain problems as time increases. And one of the goals that we're going to be trying to work towards today here is to eliminate this problem, to have an order one number of frequency domain problems that will allow you to solve the solution, the problem for all time. So what is the basic problem? On the left, I'm showing a long duration incident wave. This is the signal that one must Fourier transform in order to solve those scattering problems. And on the right, I have the Fourier transform, which I will note is highly oscillatory as a function of frequency omega. This causes a problem for us because we're going to be needing to integrate the inverse Fourier transform integral. And this means that we're going to need to interpolate this function, the incident signal function, as well as the solution in frequency domain, which means we need to resolve the signal. And since this signal gets increasingly oscillatory for longer times, this will cause problems for efficiency for the method. This is essentially what previous contributions have noticed. So to alleviate this problem, what we do is we recognize that the PDE itself is linear time invariant, except for the boundary data. Now, for the boundary data, what we're going to do is we're going to lay down a set of centers in time and then build a partition of unity of time. And so we're going to be splitting up the incident field B into little packets, BK, you can think of. And then each of these packets BK are going to individually scatter off the obstacle, and we're going to produce an overall solution that is the sum of individual scattering solutions UK corresponding to each of these wave packets. So this is the basic idea. There's no approximation yet. This is just an idea. Here's the what this looks like pictorially. So we have the same signal I showed earlier, but with a number of partition of unity functions that all add up to 1 overlaid onto the signal, and then each of these will result in an individual wave packet that scatters off of the obstacle. So mathematically, what this implies is that for the incident field, when it's Fourier transformed, it actually is a time-limited integral. And what's more, it results in a frequency domain quantity, pk slow, that is solely oscillatory in frequency domain. So what we can do is we can factor the incident field in frequency domain into a rapidly oscillatory analytical function, this exponential, and a slowly oscillatory function of frequency. Now, by linearity, this also holds for the frequency domain solution. So we have a function which we can interpolate in frequency domain numerically, and then we have an analytical, rapidly oscillatory function that we can handle analytically. I will mention that we can actually reuse integral equation solutions, or PDE frequency domain solutions, across all of these individual partitions, k equals 1 through capital K. And this is really the power that allows us to reduce the number of frequency domain problems that overall need to be solved from an order t, or increasing number, down to order 1. I don't have time to get into too much of the details today, but you can look into the details offline. So schematically, I've kind of sketched out what's going on, but maybe it'll help to see some pictures of what's going on. So on the left, I show the windowed real signal, and on the right, I show the windowed Fourier transform that corresponds to this signal. You'll notice that it's less oscillatory as a function of frequency. Here's a different time center. Similarly, less oscillatory in frequency domain. So once we've done all of that, we need to actually go back to time domain using an inverse transform. And it's worth mentioning that classical quadrature rules for this task will not suffice. For example, if one uses the trapezoidal rule, which is very convenient because you can use FFTs and so on to accelerate these computations, you will run into a problem. And that is that the trapezoidal rule implies that your numerical approximation is time periodic. That is, you're committing 100% error after some point in time. You have spurious periodicity. And to handle this spurious periodicity, what people have done in the past is they've refined in frequency. They solve more frequency domain problems, and this allows them to have a longer period and postpone this problem. But it does imply that you need to solve more frequency domain problems, which we'd like to avoid. So instead, we propose to take this frequency domain solution function, interpolate it in frequency domain. We're going to use a Fourier series expansion of the function in frequency domain. And then once we have that Fourier series expansion, we can plug that into the inverse Fourier transform integral. What we have then is integrals of the product of the basis functions of the Fourier series times the kernel of the Fourier transform. And this can be integrated analytically and therefore commit no numerical integration error. The only error is from the approximation for the Fourier series. Now, I'll mention what this results in is we can evaluate the solution anywhere we'd like in time, independent of other points in time. That is, we can evaluate it on an arbitrary grid. Said another way, there are no CFL limitations to this method since we're not doing time stepping. This is a global and time method. Once we solve the the frequency domain problems that we need to solve, we can evaluate the solution anywhere we'd like in time domain. And there's some acceleration methods that I don't have time to get into that you can look at in more detail. Here's just some convergence plots to show that the basic quadrature rule I just described works for periodic functions of frequency and for non-periodic functions of frequency as well. So the overall convergence analysis is that we have two error contributions here. We have a numerical band limit that we need to choose. We need to choose what cutoff we're going to use for the frequencies under consideration. And then we have the number of frequency domain problems that we need to solve. Now, although both of these sources of error are independent of an increasing time of interest, but it's also important that this be high order. And indeed they are. So with respect to the frequency truncation parameter, W, the error decreases super algebraically as the band limit increases. Whereas for the number of frequency domain problems, which is order 1, independent of increasing time, these are high order with respect to J. So here's a demonstration of how this works. This is that kite question I posed at the beginning of the discussion. Here it is scattering off of the obstacle. Here is on the left, a solution trace at a particular point in space. And then on the right, I show the corresponding error plot convergence with respect to delta omega. Delta omega being proportional to 1 over J, the number of frequency domain problems that need to be solved. And this is what we like to see. We see high order convergence as the number of frequency domain problems increases. Here's another simulation with a whispering gallery. You'll see a significant number of multiple scattering events that are occurring in this trapping geometry. You'll notice also some focusing that is occurring at the foci of the ellipses that bound this obstacle. One thing I'll mention is that we need to solve a significant number of frequency domain problems, since the solution in frequency domain is quite complex as a result of all this multiple scattering. But this goes on for some time. I'll show you again this plot at the end of the talk as it keeps going. Here's some demonstrations in 3 dimensions. This resulted from solving 150 integral equations for these 3-dimensional scattering problems in frequency domain. I will mention that the frequency domain scattering literature is quite vast itself, and this is built on work with Emmanuel Garza at Caltech, who was working on developing 3-dimensional frequency domain methods. So, and as far as benchmarks to existing methods, I want to share a few with you. So the codes I'm describing to you were written in Fortran and were done without any acceleration technology in the sense of fast multipole or H-matrix acceleration techniques. However, the methods I'm comparing to for convolution quadrature do use those acceleration technologies. So in some sense, this isn't a fair comparison to us. Nevertheless, for similar error levels, we see favorable computational time and memory requirements compared to the convolution quadrature methods. On the right, I show a solution trace for that results for this example. Also, for time domain integral equations, we can compare to some examples from the recent literature. This is a recent work that is high order in space and time for the time domain integral equation methods, and was shown to be stable. Nevertheless, we also observe favorable time and memory requirements as compared to these methods. Okay, I will mention that the situation can be a little bit more complicated than what I've shown so far. You could imagine that the incident field doesn't propagate in a single direction, but it propagates in many directions before it impinges on the obstacle. So you could imagine this wave impinging from many directions over time. So, for example, what I'm showing here, where we have this bump or this point source that scatters off of the obstacle, or on the right, a moving point source. And what this means is that you have to solve essentially frequency domain problems that correspond to all angles of incidence, at least all angles of incidence up to some spatial Nyquist frequency for that specific frequency. So what this means, one should really be using are fast direct solvers. And this is what we leverage. What you do is you have some sort of representative basis for what the incident field could be, solve all of those, and then reuse those solutions for those basis functions across all the partitions in time. And I don't have time to go into too much detail about this, but you can see some demonstrations here of how it works. And importantly, the fact that by using fast direct solvers, this can be an efficient method. For example, with n equals 80 solves per frequency, 80 right-hand sides per frequency, we only observe a 2.5% increase in solve time as compared to a single direction of incidence for the same problem. So this implies that in some sense, the multi-incidence case, the generic problem, is no more complicated than what I've already shown you, as long as you have a fast direct solver, which I'll mention in 3 dimensions is an active area of research. So as far as long-time 3-dimensional simulations go, I want to start talking about this problem. On the left, I show a simulation involving many, many wavelengths of propagation without increasing error for large time, I'll mention. But what I'll show on the right is the individual solution components, these individual wave packets that impinge at different points in time and scatter off of the obstacle, and then overall can be added up to produce the overall solution. However, it would be nice to know which subset of these solutions contribute meaningfully at some points in time. And that's what we're going to be talking about next. Do we need to evaluate all the windows in the sum to obtain a solution to acceptable accuracy? The answer I'm going to answer to you is no. And how do we answer that question? So the way we're going to be doing this is we're going to be looking at surface quantities. These are surface densities on the boundary of the obstacle. And a simple proposition to prove is that if you can guarantee that your surface density is small for all time into the future, it's less than some constant times epsilon, then your solution in some volumetric region is also going to be small. This is a really simple proposition to prove. It doesn't prove much, in fact, because it relies on knowing that the density is going to be small for all time into the future. To actually answer this question and make this proposition not incredibly weak is going to require a little bit of analysis, because we need to be able to guarantee that our density is going to be small forever into the future. And so the question is, can this be done? We actually answer this question in the affirmative by using something called a domain of dependence interval. So this allows us to observe on a fixed region of time history and predict whether or not the solution will be small into the future. So a domain of dependence time interval specifically is a length of time that it would take for one point on the boundary of the obstacle to communicate with any other point on the boundary of the obstacle. That is, it would be of length diameter of the obstacle divided by the wave speed. And if we can measure that the density is small for this length of time, we can actually conclude that it's going to be small into the future. And this theorem that I show on this screen is saying essentially that you can bound the density into the future uniformly in terms of norm values of the density on a time interval of the recent past. This theorem actually shows significantly more, and it's actually necessary to show this additional information, and that is that we have a decay estimate. That is that the solution actually decays as time increases. This estimate shows superalgebraic decay with respect to time as time increases. That's this t to the power 1 minus n for any n in the estimate. And we use something called a Q growth condition, which is tied to frequency domain growth of the Helmholtz resolvent operator, which I don't have time to get into right now, but it's an active area of research in the numerical analysis literature, but it hasn't previously been tied to estimates like the one I'm showing you on the screen today. Here's how the algorithm can work pictorially. So on the bottom left, you see the surface densities impinging on the obstacle. And then on the top left, you have the volumetric region where we might want to evaluate the solution. So on the right, I show a plot where if the surface densities are larger than some tolerance epsilon for a particular point in time, then you see that it is plotted in color for a specific y value, which is the time window index. So for values of time larger than where each individual time window index is active, then these solutions can be discarded or alternatively not even computed, leading to some efficiency gains. And so preliminary experiments bear out this theoretical guarantee that you can actually do this truncation and obtain errors less than your tolerance. Mathematically, what this corresponds to is a theorem which says that you can truncate your solution So you'll notice that our solution U is our exact solution, and then we have this summation of little uk from k equals 1 to capital K, except now we truncate it and we make we commit some error. What this theorem says is that you can actually bound the error for a truncation to a fixed number of solutions, u sub k, and commit a controllable amount of error. And what this means for us from a numerical analysis perspective is that we are resulting in a order 1 numerical method at the end of the day, because we've reduced the number of frequency domain solutions that we need to solve to order 1, and we've reduced the number of time domain solutions we need to compute at any given point in space-time to an order 1 quantity. And that's what this theorem is really telling us. Now, I want to end by talking about the connection of some of this decay work that I was just mentioning to an existing area of mathematics called scattering theory. And this goes back to the 1960s and 70s, where Lax, Morowitz, and Phillips showed that you can actually connect decay rates of scattering problems to the locations of poles of the resolvent operators. This is the solution operator of the wave equation in frequency domain in the complex plane. So if you can guarantee that your resonances of this operator, the poles of this operator, can be bounded away from the real axis in the frequency domain, that's this parameter alpha I'm showing here on the right. If you can show that this is bounded away from the real axis, then you have, in fact, an exponential decay estimate for the wave equation. However, if your poles actually approach the real axis, then you don't have this estimate. You can only predict that it would be sub-exponential. And what Lax and Morowitz were able to show in the 1960s is that for star-shaped obstacles and non-trapping obstacles, you do have a spectral gap. So you do have an exponential decay estimate. Now, there's a famous conjecture by Lax and Phillips that says that any trapping obstacle, which traps waves between the obstacles, such as these unions of obstacles I show here on the left, this conjecture says that they will always have a pole sequence approaching 0. This conjecture turns out is not quite true, but it's generally thought to be mostly true. So in particular, for the geometry I show at the bottom, where you have these little cubes that are facing each other and waves can get trapped between them, we know that the rate of decay of waves must be sub-exponential. However, since the 1980s, we don't really know how quickly waves decay. And one application of the theorem I just showed you that we proved is that, in fact, for trapping obstacles that have frequency domain resolvent estimates on the real axis alone, you can show superalgebraic rates of decay for the time domain scattering problem. So in particular, for these trapping obstacles I show you here on screen, where the Lax-Phillips theory predicts that you would have sub-exponential rates of decay, we actually know that we have an estimate that the rates of decay will be at least superalgebraic, which is the first rapid decay estimate for these kinds of commonly occurring trapping obstacles. So I'll just flash a few future directions of things I'm currently interested in this direction. I'd also mention that at Michigan, I'm working on some things that are completely different with Strabon and Vera Panini. And I want to thank you for your attention and look forward to a few questions. Thank you very much.